Okay, so now let's do parts C and D since they're a little bit different from parts A and B. So part C. So I'm just going to rewrite what that function was. So keep in mind that f of x was ln of x. So, and I want to ask again the same question: where are the vertical asymptotes? Now you can't rely on the idea of denominator equals 0. There is no denominator here, right? So you kind of have to know something about ln of x. ln of x is kind of one of these special functions. So how would you go about solving this problem? Like someone's typing in the chat. A couple people are typing. So some people have some ideas. Change to exponential. I can't really change to exponential because, for instance, even if I wrote e to the y equals e to the ln of x, which equals x, that still doesn't really give me information about asymptotes because now I have the equation e to the y equals x, and that's really no different from the original. I really want to keep it in the form of y equals something. Kevin says find the domain of ln of x. Okay. In fact, there's a little bit more I should ask about this. Where is ln of x continuous? Now, in this particular example, the question where is f continuous and what is the domain of f, they happen to be the same answer, right? Because we know that ln of x is continuous on its domain. Like Kevin said, that is a gnome, the interval would be 0 to infinity. So since ln of x is continuous on its domain, f is continuous on 0 to infinity. Now, why do I bring up continuity and not just the domain question? Because even if I have a vertical asymptote, I can still have that x value in the domain of the function, right? So asking what is the domain of a function does not necessarily give you information about the vertical asymptote. However, asking where is the function continuous does give you information about the vertical asymptote. Because if the function has a vertical asymptote anywhere, right? If, say, the vertical asymptote happened to be at x equals 4, then obviously the function cannot be continuous at x equals 4, right? There's no way you can have a vertical asymptote and still be continuous. So asking where the function is continuous kind of gives you a candidate. It kind of tells you where should I look for vertical asymptotes. So now that I know that the domain of this function, the domain of continuity of this function is 0 to infinity, that means there's only one possible place where this function might have a vertical asymptote. It could be at x equals 0, exactly what Marvin said. The only place where a vertical asymptote could occur is x equals 0. Now, the only question is, does a vertical asymptote actually occur there? So the only candidate for a vertical asymptote is x equals 0. Is there a vertical asymptote? Say. Well, now this is something that you can't really prove from hand. Like analytically, this is something you kind of just have to know. But we all are very familiar with the graph of ln of x. Right? So we all know this graph. So I'm now going to just say, okay, so since the limit as x approaches 0 from the right of ln of x is equal to negative infinity. So notice that at a certain value of x, 0, I get an infinite limit. So therefore I have a vertical asymptote. So since limit as x goes to 0 from the right side of ln of x equals negative infinity, x equals 0 is a vertical asymptote for ln of x. And that's it, right? It's kind of you know it or you don't. But I really wanted to bring up this example because I wanted to kind of emphasize that denominator equals 0 kind of helps you in a lot of problems with vertical asymptote, but not all of them, right? This is one where the idea of denominator equals 0 doesn't really make sense. All right, any questions about that part? Okay, so I'm going to pause the recording again just to break this up, break the video up into several pieces. All right, so now let's look at the final example. So now part D, so you've kind of been seeing a hierarchy in these problems, right? They've all been getting progressively, not necessarily harder, but definitely there's kind of another subtlety to the problem. So now part D kind of combines all the subtleties of the previous problems into one. So how would you proceed, or how would you say we should proceed? I want to find the vertical asymptotes. So ln of x equals 0, right? I mean, put the denominator equal to 0, right? That's kind of the thing we already knew. So put denominator to 0. But no solution. We definitely do get a solution for this. ln of x equals 0. There definitely is a solution to this equation. X equals 1. That's right. Now, again, I will ask the same question I did. However, that gives 0 over 0, right? So x equals 1 is actually going to be something we have to check. So let's get all the candidates first, right? Let's actually say here, get all candidate vertical asymptotes first. So one such candidate is, if I set the denominator to 0, I get x equals 1 as a candidate. Now we've seen there is another way we can get candidates. Where is this function continuous? Ooh. Well, where's the function continuous? It's a ratio of a polynomial and ln. The numerator is continuous everywhere. Continuous, all real numbers. The denominator, as we've just discussed and what Kevin just reminded of us, this is continuous only on the interval 0 to infinity. So the whole entire thing, the whole fraction is continuous only on the 0 to infinity, right? We have to take the intersection of their continuities. So, here's that. So note that f is continuous on the interval 0 to infinity. So x equals 0 is another candidate. So now let's check both of them. All right, so x equals 1. So as someone actually already noted, if I substitute x equals 1 into this function, I actually get 0 over 0. I don't get non-zero number over 0. So direct substitution to f of x gives 0 over 0. So that does not mean vertical asymptote, right? It actually means that it might be vertical asymptote, it might not be. You don't know yet. So I need to use L'Hopital's rule to actually double check. Do I really have a vertical asymptote? So let's look. So lim as x goes to 1 of this function. All this. Okay, so using L'Hopital's rule, so I differentiate the denominator, sorry, the numerator and denominator separately. So we get here 15x squared minus 4 all over 1 over x. And then substituting in x equals 1 gives me 15 minus 4 over 1 over 1. So I get 11. So in fact, I do not get an infinite limit. Right? So I can already say that this is not a vertical asymptote. Okay, Now let's check the other candidate, right? We also had x equals 0 as that candidate. Remember, x equals 0 was not coming from denominator equals 0. X equals 0 was coming more from the fact that this ln function kind of has special behavior at x equals 0. Right? ln of x, we know itself has an asymptote at x equals 0. So it could be possible that the whole thing has an asymptote at x equals 0. Again, let's actually just do the limit as x approaches 0. Technically, we have to say from the right because the domain of the function is just 0 to infinity. There's no numbers to the left of 0 in the domain. So let's just be a little bit careful about that. It won't really affect how we calculate this limit. So what do we get here? This is interesting. So what happens as x goes to 0 from the right? So clearly the numerator just gives me -1, right? That's not really the hard part. What happens to ln of x as x goes to 0 from the right? The limit doesn't exist, that's correct, but it is a special type of not existing. What would you say is this limit? As x goes to 0 from the right, just the denominator ln of x. Keep in mind, what is the graph, right? Always think about what is the graph of ln of x. Like that. Negative infinity, right. Okay, so this limit here is negative infinity. So I can now put that in here. So I get -1 over negative infinity. Is that an indeterminate form? Is it undefined? Do we use L'Hopital's rule? What would you say about -1 over negative infinity? 0, that's correct, right? If I have a fixed number, if I have a finite number divided by infinity, keep in mind what that actually means. It means some number, like -1 in this case, divided by a larger and larger and larger number. Right? If you keep dividing -1 by a larger and larger and larger number, you eventually just get arbitrarily close to 0. Right? So a number over infinity, a finite number over infinity, always gives you 0. This limit actually ends up being 0. And again, we can say, since this limit is not infinite, I'm actually just going to copy it from the previous part. Since this limit is not infinite, x equals 0 is not a vertical asymptote. So in fact, this function, we found out the only candidates for vertical asymptotes were 0, x equals 0, and x equals 1. Neither of them were, so this function has no vertical asymptotes. Just kind of surprising, right? Kind of a funky looking function. It looks like there's going to be vertical asymptotes, but it ends up there's not a single one. All right, questions. Why did you take the limit of 0 from the right again and not 0 in general? So this is kind of just a technicality. Looking back at the original function up here, remember what is the domain of this function? I'm actually going to write it out, put it in the notes. So domain here is 0 to infinity, right? Because the ln is not defined for negative values of x. So it wouldn't make sense to take the limit from the left. It only makes sense to take the limit from the right.